This is Dr. Brown. In this video, we're going to talk about how we estimate the area under curves. We're going to talk just briefly about a new notation called sigma notation, and then we're going to introduce the concept of the definite integral, which will allow us to calculate the area under curves. Now, this is just an introduction to area under curves. If we had these functions here versus x, and they look like this, we could find the area under these curves very simply. We really would not need integral calculus. For instance, if the width of this rectangle were w and the length of this rectangle were L, then the area would be equal to, obviously, the length times the width. The next figure, of course, is a triangle, and if the function here in the middle had a value of h, in other words, the height of the triangle were h, and the width here of the base of this triangle were b, then the area would be 1/2 the base times the height. Next, we have a semicircle, and if the semicircle had a radius of r, then you could see very clearly that the area would be 1/2 the area of a circle, which is 1/2 pi r squared. And then finally, if you had a trapezoid and the lower base of the trapezoid was L2 and the upper length or base of the trapezoid was L2 and the height of the trapezoid was h, then the area would be just simply equal to the height times 1/2 L1 plus L2. If everything looked like this, then we would not need calculus. However, very often we might have a function that might look like this and is not a regular geometric figure that we readily know the area of. So we need to figure out how to calculate the area under a function. Now, one of the first things we might think of is to approximate the area using rectangles. In fact, if we went back to this original function, we could obviously estimate with one rectangle that would enclose the entire figure between A and B, and that would be an overestimation of the area. The area would be B minus A, which is the length of the curve between A to B, times, say, the peak height here, and obviously we would be in error by this much. Well, if you think about it a little bit, we can do better than that. For instance, suppose we had the function of x equal to 1 minus x squared, which is a parabola pointing down. Suppose we decide to estimate it by using two rectangles, and so we start out at A, which is 0, and B, which is 1, and break the base up into um, two intervals. Um, and the width of each of these rectangles would be 1/2. And if we use what we call upper rectangles, in other words, we're going to have an estimate of the area that's going to overestimate the area. We would calculate the value of the function at this point, which is equal to 1. So the height of the rectangle is 1. So the area of this first rectangle is 1 times 1/2. The second rectangle, its width is obviously also 1/2, but we need to calculate the height of the rectangle. So we need to calculate the value of F at 1/2, which is equal to 1 minus 1/2 squared equal 3/4. And so the area of the second rectangle is 3/4 times 1/2. And so if we add all that up, we get 7/8, and our estimate of the area is 0.875. Now we can do better than that. We can use 4 rectangles. And now we look at the width of each rectangle would be b minus a is equal to 1 divided by 4, which is 1/4. So the width of the rectangle is 1/4, so we're going to multiply all the height of the rectangle by 1/4, and we're going to have 4 of them. The height of the first rectangle, again, is just F at 0 equal 1. The height of the second rectangle is going to be F at 1/4, which is just 1 minus 1/4 squared is equal to 15/16. Similarly, the height of the third rectangle is F of 1/2, which is 1 minus 1/2 squared, which is 3/4. And finally, the height of the fourth rectangle is F at 3/4, which is equal to 1 minus 9/16, which is equal to 7/16. So looking down here, the sum of the areas of the different rectangles, we sum them all up and we get 25/32. And our better estimate is 0.78125. Now I'm going to go ahead and tell you that the true area under this curve, when we start using calculus by next period, is going to be exactly 2/3, which is 0.667. And you can see both of these estimates have made an error here, and you can see the error that we're getting when we do the estimate. We're missing the amount I'm shaving, or we're overestimating by the amount I'm shading here. But we're going to show with integral calculus how we can calculate exactly the area. Now we're going to do one more example. Suppose we want to find the area under the sine curve between x equals 0 and x equal pi. And obviously you see the sine function, uh, the upper lobe between 0 and pi. And suppose here we want to use 8 rectangles. So we're going to define the width of the rectangle to be equal to b minus a over n, where n is the number of rectangles we're using. In this case, it would be pi minus 0 over 8 equals pi over 8. So as you can see down here, we're going to be multiplying the height of all the rectangles by pi over 8 and summing them all up. So what we need to do is find the height of all the rectangles. So you can see I've drawn 8 rectangles. Obviously, the height of the first rectangle is going to be sine of pi over 8. The height of the second rectangle is going to be sine of pi over 4. The height of the third rectangle is going to be sine of 3 pi over 8. The height of the fourth rectangle is going to be sine of pi over 2. And the height of the fifth one is going to be sine of pi over 2. And then as we go down, the height of the sixth rectangle is going to be sine 5 pi over 8. The next one will be sine of 3 pi over 4. The next one will be sine of 7 pi over 8. And here it's just a simple matter of putting this in your calculator. Sine of pi over 8, sine of pi over 4, all the way down to sine of 7 pi over 8. Why don't you put this in your calculator and multiply the total by pi over 8? And you get that the area under this curve is estimated to be about 2.365. Now, within the next week, we're going to show how to calculate exactly the area using calculus. We won't be using rectangles anymore, and we will see that the true area will be exactly 2.0. So you can see we have an overestimate of the area of 0.365. Now this next curve is just to show you that you could use even more rectangles and get less area, less error, and get a much better estimate of the area under the curve. Now the question is, how about lots and lots of rectangles? Suppose you decided that you wanted to get a very accurate estimate, and you wanted to draw, and I can't draw these rectangles too well, draw rectangles sort of like this. I'm not going to draw them all. If you drew all the rectangles, you see you would draw rectangles that had a height, and let's say this was x sub k here. The height of the rectangle would be alpha of x sub k, whatever that value of x sub k was. And you would keep on drawing rectangles, and if you had all the time in the world, you might draw 100 of these. This might be x sub j, and this might be, b would be, of course, x sub n, the nth rectangle, and the height of the last rectangle would be f of x sub n. And this could get very tedious. But you can see if we had lots and lots of rectangles, the arrow we make would be pretty small. And if we let n go to infinity, then theoretically the arrow we make would go to 0. So that's what we're going to try to do when we introduce the concept of the definite integral in another couple of slides. First, I want to show you a little bit of new notation, which will maybe lower the number of things we have to write down. And it's called sigma notation. It comes from the symbol sigma. This is the Greek letter sigma, and it means sum. And it says to sum up this formula a sub k. This is a formula for the kth term, and the k equal 1 really indicates the index of k, and this is a lower index. In this case, k is starting out at 1, and the number at the top is the upper index for k. And this notation just simply means add a1 plus a2 plus a3 all the way up to a sub k minus 1 plus a sub k minus a sub k all the way up to a sub n. Now, to give you an example, suppose a formula was just simply k. This means just to plug in first k equal 1, then k equal 2, then k equal 3, all the way up to k equal 5. So the terms would be 1 plus 2 plus 3 plus 4 plus 5. Those are all the terms, and you add them up, and you get 15. Now, let's take the next example. It goes from an index of 1 to an index of 2, and plugging in 1 first, we get 1 over 1 plus 1, plus plugging in 2, we get 2 over 2 plus 1. So this is equal to 1/2 plus 2/3 equals 7/6. Now notice the index, the lower index, doesn't always have to start out at k equal 1. It could start off at k equal 4 and go on up. The second example would be simply plugging in 4 and then plugging in 5, and so we get 4 squared, which is 16, divided by 4 minus 1, plus 5 squared, which is 25, over 5 minus 1, which is 16/3, plus 25/4, which is equal to 64/12, plus 75 twelfths equal 139 twelfths. Now in this next slide we're going to introduce the concept of the definite integral, which is going to help us not have to do a lot of the summation that we were just talking about. Let's say that we have a function f of x, and let's break it up into a number of rectangles, and we're going to let the width of each rectangle be called del x, and it's going to be b minus a divided by n. In other words, it's the length of the distance between the first point we're going to use in our integral, which is a, all the way to b. It's the last point, and we want to calculate this integral. Notice that we have areas here where the length of the rectangles are negative. In other words, the function is below the x-axis, and the area of these rectangles is going to have a negative value. And the first point we're going to consider is a equal x naught, or x equal x naught. We're going to look at x1, which is a plus 1 times delta x, and of course x2 would be a plus 2 times delta x, and we keep on adding rectangles until we have n rectangles, and finally we get to b equal x to the n. And then we're going to pick points within each rectangle. C1 will be an x value that's within the first rectangle, and the height of the rectangle will be simply f at C1. The height of the second rectangle will be the value of the function at x equals C2, which you can get from the value of the function f of x. And we've drawn here the k minus 1 rectangle, and have the point c sub k minus 1 at this point, and find that its value is f of c sub k minus 1. And then when we get to c sub k, we got f of c sub k would be the height of the kth rectangle. And finally we get to the end, and we have f of c sub n, which is a value of the function at x equal c sub n. And what we do is we sum up all of these rectangles, and the sum would be the width of the rectangle, which is delta x, times the height of each rectangle, which is f of c sub k, and we sum from k equal 1 to n. But then we take the limit as n approaches infinity. And what we get is a new notation here that we're going to call the definite integral. it looks like the symbol for the antiderivative, which we've already looked at, but it's simply called the integral from a to b of f of x dx. And the delta x becomes dx, and x is the variable of integration. Now we're going to do some problems in class and talk about some properties of the definite integral, and we're going to show you using the fundamental theorem of calculus how to do this, and we will do that next time. But first, I want to reiterate what the definite integral is. First of all, it's summing up n rectangles as n goes to infinity. Actually, you wouldn't even want to do probably 20 rectangles. But the easy thing that we're going to have is when we use integral calculus to calculate the definite integral, which allows us not to have to add up all of those n rectangles. So now we're going to talk about some properties of the definite integral. What does it tell us about a function? First of all, if you have a function of x, and just suppose for this example that the function is above the x-axis, that the area under the curve is going to be the integral from a to b of f of x dx. And if you had, for instance, a piece of land along a highway, and f of x represents the distance from the highway to the fence in the back of your property, then you could get the area that you have between a and b by calculating the definite integral. Another example would be, suppose P of t was a profit versus time of your business, and you went from like 3 years to 10 years, and you started off with a certain profit. The profit went down, and in fact over a period here you got negative profit, or actually have a loss, to a better time when you got profitability again. The total cumulative profit P would be the integral from 3 to 10 of P of t dt. Notice the variable doesn't have to be x, it can be t. And we'll be taking antiderivatives of function of t, functions of x, and so forth and so on. Okay, the last thing we're going to talk about here would be some properties of the definite integral. Let's suppose we have a function f of x that goes from a to b to c. And first property is that the integral from A to C, which in this case would be the area under the curve between A and C, is simply going to be the integral from A to B of f of x dx plus the integral from B to C f of x dx. The next property is that if we integrate a function between A to B of f of x dx, that it's equal to the negative of the integral from b to a f of x dx. And we'll talk about this a little more in class. And then the last property I'm going to talk about is the area between curves. If you had a function f of x and then a function g of x, both going from A to B, and suppose you wanted to know the area between the curves, the area between the curves, that's the area here between the two boundaries, it's just going to be the integral from A to B of f of x dx plus minus the integral from A to B of g of x dx, which is simply equal to integral from A to B of f of x minus g of x. So really we're going to see that it's going to be the upper curve minus the lower curve and integrate the function between the two limits, and you get the area in between the curves. And that's the video.